We're into the third unit on the mechanics, and what I want to start by talking about is energy, and you've already done a little bit of that in your previous science. We all know about gravitational potential, mgh. Kinetic is half mv squared. We've learned about a new one with springs. This is potential elastic, which was 1/2 kx squared. And there's a new word which we often see associated with these types of energy, and that's mechanical. Okay, it's related. Mechanical is related to an object's motion or position, and so these are types of mechanical energy. So sometimes they might say, what's a change in mechanical energy? You're looking at just these types of energies. You're not looking at heat. We also had this formula, work equals force times distance. We've got a power formula related to energy. Power equals energy divided by time. Work, you should be thinking of change in energy. So it's an energy. We use the word work and it's a little bit strange. So work is change in energy. Now these energy principles are very, very useful. And these formulas like this, often you can calculate things using these principles much easier than you can using the other kinematics and stuff like that. So it's a little bit like that one that we do in, again, year 9, where we have an object and it's dropped from a height. And you say, how fast is it going to go? And you go, okay, I know that it's got this much potential energy, mgh. And I know if that all gets converted, then at the bottom here, it's going to have half mv squared as an energy. And you do your cancelling of your masses and you work out your velocity. You've used a principle. And the principle you've used is conservation of energy. You've said energy is never created or destroyed. And so assuming that all the potential energy gets converted into kinetic, which it wouldn't in real life because of drag and stuff like that, then this formula is going to hold true. Very powerful principle that we use there. Work equals force times distance. That basically also says that if I've got an object and I apply a force over a distance, maybe 20 meters, so this could be a 10 kg cannonball or something, I apply a force, a constant force over that whole distance. Then all I do is multiply the force times the distance, gives me the energy change or work done. And what you'll find, and this is really cool, see when a net force acts on an object, it's going to cause an acceleration, and an acceleration is going to cause it to have a change in velocity, and a change in velocity is going to cause it to have a kinetic energy. So when we do this over that distance, we will find that we will end up with a velocity that's basically going to be related to this. What I said there was not that clear, was it? Basically, force times distance. Force over that distance is going to give you kinetic energy, half mv squared. So again, we could work back and figure out the velocity. Now that's simpler than doing this, where you go, okay, we've got this cannonball, 10 kgs, I've got this force acting on it. I can go force equals mass times acceleration, right? I know the mass, I know the force, I got the acceleration. I've got now the acceleration, and I can say, okay, if this acceleration acts over this distance, what was it? I forget what I said the distance was. Then I can now work out, hopefully, the velocity, right? And we'd have to go to our kinematics. Vs squared equals vi squared plus 2ad, acceleration, distance, vi was 0. I could figure out the final velocity, right? And then that final velocity would be the same as the one I just figured out there. F times d equals half mv squared. So in one case we have to use kinematics to work it all out. In the other case we have to use conservation of energy, and the whole work equals force times distance. So it's really cool that conservation of energy can give us those principles. Now the thing about work is, and again this is a level 1 principle that you should know, work equals force times distance. the force must be in the direction of the motion. So if my force is not in that direction, then no work is done. So it's a little bit like if I've got a rope and I'm swinging something, this is looking down and it's going in this big circle. This is centripetal, so it gets back circular. The velocity is that direction, so the motion is in that direction and the force is in that direction, centripetal force. There is no component of the force in the direction of motion, so no work is done. So if no work is done, there is no change in mechanical energy. So you're applying this force the whole time, but there's no change in the mechanical energy. So the kinetic energy of this object will stay the same. But you're having to exert a force the whole time just to keep it going in that direction. So that's work and energy. A lot of other problems you can use for this. I think it's really quite interesting. We could use it with an object going up a ramp. We can work out the forces here, right? We've done it with our vectors. So if we've got a box of something on there, we can split that into its vectors and we work out pretty quickly that the force of gravity that way is equal to mg sine theta, if that's theta, right? So if I can apply a force in the opposite direction of mg sine theta, once I get it moving, okay, it's going to go up the ramp at a constant speed because there's no net force, and it's going to change its height. And so what I'll be able to say then is the force times the distance, F equals mg sine theta. If I multiply that by d, multiply that by the distance, that's going to be equal to the change in energy, mgh. So again, force times distance equals change in energy, but the force must be in the direction of the motion. Okay, that's enough on that one.